Hello everybody, Greg is here. I would like to start by remembering the great chemist Professor Raphael Mechoulam. He was the guy who discovered the active ingredients in cannabis, and it was a great scientific breakthrough in the 70s, and he continued to work on this topic. He is responsible for all this great field of cannabis research, which had a huge impact on the medicinal chemistry and many other things. The video of today will be dedicated to one of my favorite topics, which is biradicals. Biradicals are molecules which have two unpaired electrons, which are represented in this picture by those arrows. Simple radical, which has one unpaired electron, usually very unstable molecule. Biradicals, considered to be even more unstable, but depends a lot on the interactions between those two electrons. One of the reasons also I wanted to talk about this topic is when I just looked at Angewandte Chemie journal, there were like 3 brand new papers dedicated to biradicals, and I just thought that I'll group those papers and describe in one video. Please don't forget to press the like button, to subscribe to this channel, to write a comment if you think that something is wrong or if you like this format of several topics in one video. Press the notification bell so you don't miss future videos, and share it with anyone who might be interested in this type of content. By the way, in the end of this video there's going to be some very exclusive content which was not published anywhere, so stay tuned. So I would like to start with showing the d radical, which is stabilized by phenyl groups with halogens. And that's the classic way to stabilize radicals. The first radical that was discovered in the beginning of the 20th century was stabilized by phenyl groups. When you add halogens to the phenyl groups, this type of radicals become so stable so you can isolate them by chromatography, expose them to air, to water. And I'll use this example to explain the meaning of those arrows. And I don't want to go into physics of why it's singlet and why it's triplet. But in the singlet state, the spins of the two unpaired electrons are opposite. One electron cancels the magnetic moment of the other, and that means that they interact through bonds. Those green and blue shapes, this is the calculated spin density distribution. And you can see that on every atom in this molecule there is some spin density. Now look at this ring in the middle. When this ring rotates a little bit, this interaction disappears and each electron becomes independent, and then triplet forms. So usually the gap between singlet and triplet state are pretty significant, but in this case it's very small. You can see here the electron paramagnetic resonance signal. It becomes magnetic already at room temperature, and as you raise the temperature you have more triplet over singlet state. This is the X-ray structure, by the way. But the reason this radical was published in Angewandte was not because it's so stable, but because of its photophysical properties, or specifically the luminescence. Luminescence is when a molecule can absorb light or photon at one energy and then emit another photon with lower energy in a visible spectrum. So in this case, the absorption of the light happens because of the excitation of the electron from the highest orbital, and the emitting happens when the electron falls back. The interesting thing about the biradical is that it has the option of excitation of an electron from the second highest orbital, which provides usually very different emitting patterns. So when the singlet state is excited, you have one band. When it's a triplet state, the electron which is excited first is from the orbital below, from here, and you have a second band of emission. And this behavior can be observed both in solution and in a film. Now this can be used in many different applications like organic light emitting diodes, sensors and other things. One last thing I want to say about this particular slide is about this upper picture, because it will make a good transition to the next paper I want to show. So here you see 3 structures, but actually those are 2 structures. So this and this are one, and that's indicated by this single arrow with two heads. This is a superposition of those two structures which exist at the same time in the same molecule. And that's what was shown on this electronic structure. It's just electrons are delocalized in the way that both of those representations are equally valid, but it's actually one structure. And here you see two arrows. That's when triplet forms, when this benzene ring rotates. And that's a different structure. And in this particular case, the energy between those two structures is pretty small. In the other diradicals I'll show, gap much larger. The second paper I want to show is about the diradical, which features two antimony atoms. Antimony is deep below nitrogen in the periodic table. It can participate in some unusual bonding. So that's one thing that this group takes advantage of to synthesize the biradical. Second thing is the aromaticity. Okay, just let me show the molecule. There's two resonance structures. In one, the aromatic ring is here in the center and there's no unpaired electrons. But in the second structure, the aromaticity goes to the side rings though here with nitrogens. So this way the electrons delocalize. It's a singlet structure. The energy gap to triplet is high. Here you can see the X-ray structure and here's the spin density at the highest occupied orbital. Probably even more important than the biradical structure here is the second resonance structure, because this central ring is a benzene type ring, and with such heavy atoms and as antimony, those type of structures are considered to be almost impossible. So that's the first of its type. Another interesting thing about this molecule is its reactivity. So with disulfide or diselenide, it reacts like a biradical. So selen or sulfur adds on each of the antimony atoms from this compound, and that's a typical radical reaction. And the second reaction is even more interesting because it features a transition metal, molybdenum, and again it reacts as a diradical. A conclusion from this paper: if you want to get a really unusual benzene structure, you need to consider making a biradical, and then you'll have two unusual structures in resonance. The last paper I want to show today is coming from my alma mater, the Technion in Haifa, Israel, and it is about a cubic molecule made of germaniums. And I know that in the previous papers I showed, I didn't speak at all about synthesis, but in this particular case I have to say something, because look, this complicated, beautiful cube forms from those two very simple reagents at very simple conditions. There's nothing special. How it forms? It's a very interesting question. It requires further research. It's based on elimination of a silyl group. The RH is this silyl group with the hydrogen from each of those precursors. So the simplicity of this reaction and the high yield is an important part of why it was published in Angewandte. But of course, not only because of that. First of all, yeah, that's a cubic molecule. It's green because its crystals are green. And it is a singlet biradical because germanium has 4 electrons on the outer shell, but each of those red atoms contribute only 3 of them to the bonds, and 1 electron on each of those is not bonded to other atoms, and this is why it is a singlet diradical, because there's no EPR signal. There's no magnetic properties to this molecule. This is the X-ray structure, those germanium atoms without a group bound to them. And this is the highest occupied molecular orbital. That's how those two not bonding electrons look like. This is the space they occupy. Now let's take a look at how this cube reacts. Ta-dam! So with dichloromethane, it's a typical radical reaction. Each germanium obstructs a chlorine atom. And with water, it splits water. And that's a little bit surprising to me. That means there is a polarization. They did something even better than this. they did a single electron reduction, added an electron to this cubic molecule, and got a stable anion radical, also able to isolate it with the sodium countercation and get an X-ray structure. So that's an X-ray structure of an anion radical of the cube. Now remember the molecule of the year 2022? There was also a cubic molecule made of carbons with fluorines on the periphery. When you reduce it with one electron, the electron forms a cubic electron density inside the cube. How the electron looks here. This is the spin density, not cubic at all. Still, there is significant portion of the electron on each of those naked germanium atoms. And this red thing in the middle, it's rather a wavy toroid. Here's a different picture on a different angle, on a different model. You can see this ring. Isn't it beautiful? Oh my goodness. Remember, I promised you an exclusive content in the end of this video. So one of the authors, Roman, sent me some pictures of the crystals. Here they are. So these are the green crystals of the original cube. Look at those. And those yellow crystals are from the anion radical molecule. Those pictures were not added to the supporting information, and I think that's wrong. I think every paper that feature crystal structure, especially if the crystals have some color, they should add the picture of the crystals to the supporting information at least. People deserve to see beauty. I hope you enjoyed this content. Don't forget to like and share, and don't forget to support Ukraine. Thanks a lot and have a great day.